In this example, we're going to do the same thing as before. However, this one is slightly different in that if we take a look at the shift factor inside the brackets in there, we can see that this is a horizontal shift of +3. So what that means is my center is going to be at 3. So that's one thing to notice. We're still going to do our ratio test here because we want the radius of convergence. So I'm going to set up my ratio test as the limit as n approaches infinity. We're going to have in the numerator we're going to end up with our an plus 1. So we end up with x minus 3 n plus 1 over n plus 1. And in the denominator, we have our x minus 3 to the n, and that's all over n. And we're looking to see where this is going to be less than 1. Okay, and that's going to help us establish our radius. So I'll group together my terms. So limit as n approaches infinity. I'm going to group together my x terms and my n terms. So my x terms, we end up with x minus 3 to the power n plus 1. So I'm just going to write an extra x minus 3 factor. In the denominator, I have x minus 3 to the power n. Grouping that all together, we can see that the x minus 3 to the power n's cancel out. We're going to group our n terms together, so that n over n plus 1, and we'll group that all together as well. And that has to pass our ratio test, so that has to be less than 1. So we can cancel out a few things. The x minus 3 to the power n's are going to cancel out. We're left with x minus 3. That's the x part of this, of our power series, or our power series function. The n over n plus 1, that's going to simplify to 1 when we apply the limit. So we end up with limit as n approaches infinity. We have an x minus 3 factor, and then the n over n plus 1, that's going to be equal to 1. So then we can then apply the limit or evaluate the limit. So we have x minus 3 times 1, and that has to fall between -1 and 1. So that's our ratio test. Because of that inequality, we're going to have the left edge is going to be -1. Oh, so that's not our right edge. So our radius is going to be 1. So we're going to, from the center, we're going to go 1 to the right, 1 to the left. I want to solve for the edge. So I'm going to add 3 to both sides of that inequality. So I end up with x is less than 4. And do the same for the left side of this inequality. So I'm going to add 3 to both sides of that, and I end up with my left edge is going to be at x equals 2. So then we've established our center is equal to 3. Our radius is equal to 1, and that's based on our ratio test. Now we have our interval. Our interval is now going to look like this. We have a center at 3 so far, and then our radius of 1 to the right. Okay, we have an endpoint here at 4, and then we have 1 to the left. Our endpoint then is going to be at 2. So we need to test those endpoints. Okay, so at this point, we're going to test the right-hand endpoint of x equals 4. Now the way we do this is we plug it back into the original series. So our test, we're going to test the endpoint x equals 4. Okay, so when we test x equals 4, we end up with this. The sum of n equals 1 to infinity. When we plug 4 in, we get 1 to the n, which is basically just 1 over n. And then this is going to simplify to just a harmonic series. And we know that the harmonic series diverges. Okay, so we have our, when x equals 4, this is what I've done down here. When x equals 4, the series becomes this harmonic series. It's a diverging series. So this is divergent. So we keep that as an open circle, okay, as in our interval notation. That's going to be an open right-hand interval. Move that down here. So our interval so far looks like this. The right-hand side we've tested. We're going to test the left-hand side. We're going to test this left-hand side by plugging in x equals 2. So when we substitute x equals 2 into that original series, okay, we're going to have x is 2 minus 3 to the power n, so that becomes negative 1 to the power n over n, and this is an alternating harmonic series. Okay, so that's what we have down here, our alternating harmonic series when x is equal to 2. Alternating harmonic series converge, so then we can make this convergent. Notice that we didn't do any kind of formal test to determine that. We just need to determine divergent or convergent by any means. Okay, in this case, there was a formal test was not necessary because these are standard series that we already know. So we then have a convergent right-hand endpoint, or sorry, left-hand endpoint. So we're going to fill that in. So that is a half closed interval or half open interval. And we know that on the right-hand side, it is divergent, or it doesn't include that endpoint. So at x equals 3, we know that, so at x equals 4, at x equals 4, it was open. On the left-hand endpoint at x equals 2, it was closed. So this is a half open or half closed interval. We can write it like this. Okay, we can show this with our inequality. So it's going to be greater than or equal to 2 and less than 4. Okay, and we can show this on our number line as well. We showed it on our number line. The center was going to be at x equals 3. Okay, so then we can draw it in like this at x equals 3. That's going to be our center. Our radius was 1. So at 4, we had an open interval. And on the other side, at x equals 2, we have a closed interval at x equals 2. So again, we want to do a ratio test to start. That just establishes our radius of convergence and allows us to determine our interval of convergence once we solve for x, going from there to there. And then from our center, we can establish our center as 3, our radius is 1. Okay, we can test our endpoints of 4 and 2. When we test 4 and 2, we see that at x equals 4, when we plug in x equals 4, we get our harmonic series That means it's divergent. It's an open endpoint. When we substitute in x equals 2, we get an alternating harmonic series. That's convergent. So we get a closed endpoint at 2.